In the previous video, we showed XANES analysis with linear combinations of other XANES spectra from samples of known coordination or oxidation state. And we also talked about using principal component analysis to decide how many different components make up a group of spectra. In an earlier video, we showed how to model and fit pre-edge peaks as a way to measure oxidation state from XANES data as well. In this video, we'll continue with that discussion of XANES and pre-edge peak analysis, but with a different set of data and with slightly different emphasis going down the next step of what might be called machine learning. Hi, I'm Matt Newville, and this is part of the video series for using Larch for XAFS analysis. In the example here, we'll focus on vanadium K-edge XANES in a variety of samples of different coordination and oxidation states. Here I'll read in these spectra. It's about 28 different spectra we have here. We could, and this shows a common set of results for vanadium K-edge XANES, that there's this very large pre-edge peak for highly oxidized states, vanadium 5+, like chromium 6 or manganese 7 has a very large pre-edge peak, and as you change the oxidation state from 5 to 4 to 3 to 2, this peak decreases in intensity. And in fact, you could use, and many people have used, a fairly straightforward measure of the relative intensity of that peak as getting oxidation state from a XANES spectra. For this data set, though, I'm going to just make sure that it's all normalized well. It's often a challenge. Actually, as I mentioned earlier in earlier videos, it's important to have the XANES data well normalized in order for any of the XANES analysis techniques that we use as spectroscopy to be reliable. In addition, and something I may not have emphasized enough in an earlier video, it's also important to make sure that the energy scale is consistent among the different spectra, so that they are aligned in energy, sharing the same energy axis. Maybe data from different beamlines or different data collection times would need to be carefully calibrated to one another using a known standard. For this data set, these are fairly well calibrated. And you can see we have a variety of spectra, variety of oxidation states for vanadium, and we also have a variety, as you can see, of different sample sets. So if we look at all of the sets in this LW series, I'll select down below. Then we have these giving a nice range of spectra for vanadium at different oxidation states. I could do the same with this series of FAD data sets. So just these here will also show this is sort of a cleaner data set, maybe a better data set to start with. You can see a few things. First of all, that there's a general trend of changing the oxidation state from fairly oxidized to fairly reduced. And also, if you were to imagine that this was just a combination of two different spectra, two different basis spectra that were adding together as just a single variable, what percentage of n member A and n member B, then there might be points like this point here, which is close, that would have that would be constant in energy. And you can see that that's almost the case for this point and this point. These isobestic points are almost, those are almost isobestic points where the range of spectra is the range of change in spectra is very small. So in fact, I think that you could guess that if we were to ask principal component analysis, how many different spectra there were that make up these 5 spectra, how many different components there were, there would be a small number, maybe 2, maybe 3. And in fact, we can go do that. We can just check with principal component analysis. We'll build a model from these group of spectra, and you can see that this says that there are 3 components from the 5. And in fact, if we look at each of those individually, those are the mean in the first 2, and then this third one here is maybe is a maybe on whether that's going to end up being important. So for sure, we see that there's 2 components and then maybe a third for this data set. Similarly, we could look at these other sets of data. So none up there. So these sets, this ALL, Allende set, again, there's a nice range of oxidation state and a point where they almost match perfectly. We could do principal component analysis on those. I think it's 9 spectra for this set. And here it looks a little bit more like there's some more variation, but if we look in detail, we see that actually these first few are clear and everything else is a little bit noisy. So maybe, again, there might be a third or a component, but maybe it's reliable to think of those as only 2 separate components, or three separate components instead of 4. And then finally, we have another set here. Actually, we have another set and then one of a single set. So all below, select those and plot those all together. Again, we see a range of spectra, and this one spectra is highly reduced. So as shown earlier, we could certainly do principal component analysis, linear combinations of n-member spectra, say take these 2, and you might know the oxidation states of these 2, and then take the rest of them as linear combinations, and that would work reasonably well. But for this data set, there's another thing we want to look at, and that is that we have, as you can see from these, in the names of these data sets, there's some information about the sample, how it was grown, and then NNO and a number, and that number is the fugacity, or oxygen partial pressure, relative to the nickel-nickel oxide buffer. For geochemists, this is a way of measuring how much oxygen is present in the sample, and like pH, it's a quantifiable number. It's actually very similar to pH. It's a log scale of fractional occupancy of oxygen. And it's used as a proxy for or it's used as a measure of how much oxygen is in an environment. So for Earth science, the surface of the Earth is wet and full of water, and the center of the Earth is solid metal iron. And so there's a redox potential throughout as you go deep into the Earth, reducing conditions in the core and upper mantle, or lower and upper mantle, and then fully oxidized as you get to the surface. And so a measure of oxygen partial pressure, fugacity, is a way to measure, is an important measurement for Earth scientists. And so for all of these spectra, we actually know a starting value for what those numbers should be. And one of the questions then is, can we infer that from the XANES data? That's actually the question that one of the most pressing questions for doing XANES analysis in these kinds of samples, is learning what the fugacity is. And you can certainly fit the pre-edge peaks, get out the oxidation state, and then map that oxidation state to fugacity. But since it's quantifiable, we might also just ask if we can get that directly from the spectra and not have to first get the oxidation state and then work out the fugacity from that, because there might be other variables involved. In fact, these spectra are all a little different, so there might be other factors involved, characteristics of the sample that affect the XANES spectra, but really encode the fugacity. So if we just take, for example, a set of spectra that all have about the same fugacity, say plus 1.3, 1.7, 1.8 from the different, maybe 2 from the different classes of samples, we can see that those are actually all pretty similar. Those are highly oxidized. And if we do the same, we say perhaps the ones that are close to -3, yes, there's a -3 and a -3 here, this one, and then these are also all pretty similar and much lower oxidation, but there's still some differences between them. So one of the things we might want to do is to encode this number and see if we can extract that from the set of data. So we can do that that's one of the first approaches to machine learning, is to look at some observations, some spectra, and from those extract an external variable. That could be anything you know about the sample, but including, say, oxygen fugacity, which is important for really the value you want to really be able to extract from the data. So to do that, there's a regression panel, and that's just linear analysis. That's just mapping of the spectra to this single value. So to do this, I'm going to take this nice series FAD and use the selected groups. So that's there, and then I could put in the value. So I could just type in that this one I know is 1.7, and this one is minus 0.7, and so on. I can also load a CSV file, so I'm going to do that. We have a CSV file, FO2 for FAT only. That file looks like this. It's just a simple CSV file that has the name of the group and the fugacity value. So those are just the same. You can see that, and I'll just read that in, and it fills in this form so that those are all available for that. And now I can take this and train this model. So this is a beginning of machine learning language that we train the model. We fit this to identify the characteristics of the spectra here. So there's the mean and the spread in the data that represents all of the data, and then those are like components, in principle components. It's part of a partial least squares analysis. And then on this plot, we've plotted the observed experimental data and then the predicted value from these for each of the different data sets. So with this one latent variable, it works pretty well that these are all predicted. But then again, we started with these, so this is what we told it to do. And the real question is, can we use this model then to predict the correct values for fugacity from any of these other spectra? And then if that worked out, or to the extent that worked out, it would give us confidence that we could use that for analysis of other samples. I should say that there's a couple of other variations on how this could go. So you could use a lasso technique or partial least squares. For most of what I'm showing you here, it doesn't matter in much detail what linear analysis method is used. You still map each of these spectra to a single value that is in a range. And you can also see, even from this predicted level and sort of the value here, it's labeled as valence, just as a name. You could be mapping valence, you could be mapping fugacity, EH, pH, the fractional composition of a compositional measurement of some other impurity or some other phase. Anything that's quantifiable could be used. We just called it valence here as a proxy bit. This is the FO2 compared to the NNO buffer. So let's just go, now that we've trained that model, let's go look and see if I can select a few of these spectra here and say predict the variable for the selected groups. So I'll click on that, and that then for LW plus 20 at NNO plus 1.3, it predicts a value of 6.3. And for at plus 3, it predicts minus 0.4. And at minus 0.7, it predicts minus 0.1. So you can see that it's close. The trends are right. And there's a difference that's maybe a systematic difference of about 1 or so of these log units of FO2, which is actually probably about the uncertainty or the level of uncertainty that you can get from this technique. Certainly you can predict over a wide range, over several orders. These are all log units, so over several orders of magnitude in this value, and you get a value that's, say, with an accuracy of about plus or minus a half to plus or minus 1. So that's pretty good. That's useful, and it's very simple to do. We just took our training set, and we can apply that to predict the other variables. So just out of curiosity, let's go try some of the other samples. I can just select none above this. Let's just try it for all of them. Now that we've trained this, we trained with, I should say, we trained with 5 data sets, and we're going to predict 20 or so. And it does, while it's training the model, it does cross-validation. So it'll take 1 or 2 out, replace it, see if it predicts it. It'll do all of those steps to make sure that the data is cross-correlated and so on correctly. I'll also say that in the language of machine learning, or often the language of machine learning, it's important to whiten the data, which is to say, like we did for principal component analysis, take the mean and then subtract that off and make sure that everything is scaled correctly. For applying XANES data to any of these machine learning techniques, it's important then to do exactly what we talked about earlier, and in every time we've done XANES analysis, and that is to make sure the data is normalized, goes from 0 to 1 correctly, and also that the energy alignment is correct, consistent among the data sets. You'll also need to do the machine learning, we'll also need to interpolate the data onto a common array of energy points. That's easy to do, and so is automatically done here. You don't need to do that yourself if you are importing data into this. Anyway, so let's continue. I'll just predict the rest of these, and let's see how it works. So for the LW series, it seemed to work pretty well. For the AL series, what should have been +3 is 2, and 1.4 for 2. So it looks like here we're also off maybe by a scale factor, because as we get to 0.8 is pretty good, and 0.1. In fact, you can see that the FAD data we started with had a limited range, or a pretty good range, but a limited range of fugacity values from -8 to 1.6 without a whole lot of richness to its sampling. And so at the highest end, which we didn't have any real data for, it does a little worse. We didn't include much data that was very highly oxidized. So this says it's more oxidized than anything in its training model, but it's difficult for it to tell it's completely oxidized. But then at the more reduced end, where there's actually more sampling, it does a pretty good job. And so also for this DUF series, which actually has some of the most oxidized data sets. Again, the oxidation state is predicted to be a little bit on the low side for the most oxidized. And you can also see for this data set, which is interesting, that there's 2 samples that are nearly the same oxidation state of fugacity of 0.25, and the spread there is 0.7 between them. So that's a reasonable measure of the uncertainty inherent in this value. 0.7 or so. Here for -1 for NNO -1.71 and -1.72, it predicts a value of -3. So there may be some systematic differences. Oh, here's a repeat also that those two should be about the same, and it is, but it's also pretty far off in log units, as if perhaps this data set, I'll say without any accusation, perhaps this data set should be investigated. Maybe there's a systematic difference between the way these samples measured fugacity and the other ones did. So for most of the other ones, it seems like there's just a reasonably constant offset of about ±1 log unit, and pretty good agreement over the scale. And for this one data set, it looks more systematically different. For the most reduced end member of the set, since this also has FAD, so that's actually a similar composition sample, and its fugacity range was in the same range as the training set. Actually, it does a pretty good job on that one. Again, -6.9 is predicted to be -7.3, which is sort of within our acceptable uncertainty of something like 1/2 to 1 log units of fugacity. So I think this is a relatively short presentation compared to the previous one, but I think that gives you an indication of what sort of things might be able to be done with linear analysis of XANES beyond just linear combinations to say that 2 spectra are the are a linear combination of two other spectra, and from that determine oxidation state or chemical environment. But here you can use a range of data sets to predict some other external variable value. So whether that is pH or EH, or again, some composition or some reactivity measurement, some measure of what your sample does, its efficacy as a drug, say, or its ability to change its environment, and so on. That might be something that you would want to consider being able to analyze from your data sets. And again, with a simple training, that can be done and applied in a relatively easy manner to a wide range of data sets. So I hope this was clear. I also can imagine that it will be hard. You might be scratching your head and wondering if you can actually apply this to your data sets that you have right now. And maybe that would be hard to do, but I hope that at least you keep this in the back of your mind as something that you might be able to do, and the kinds of things that XANES analysis can be used for. If you have any questions or comments or about this or any of the other videos, leave them in the comments below or contact me and let me know what you think, and I'll be happy to try to answer any questions. So see you next time. Thank you.